Okay, welcome to Bob's Z-score video. This is my third attempt at making it because I'm bad at speaking. But I promise it makes sense. So, um, firstly, this is what a graph is going to look like. It's a very crude version of the graph, but it's a bell curve. Each of these means something. So, right here in the middle, we have our mean. And then each of these is a standard deviation mark. So this is 1 standard deviation away from the mean. This is 3 standard deviations away from the mean. This is -2 standard deviations away from the mean, so on and so forth. Okay, and if we fill that out, corresponding to question 3, we know that the mean is 500 and that the standard deviation is 100. So each of these increases and decreases by 100. So like, for example, this would be 400. 400. And this one would be 200. And this one over here would be 800. So on and so forth. Bell curves usually only go out 3 data sets, by the way. So you don't need to draw any more than this. You don't need to go to 900 or 100 or anything like that. What is a z-score? A z-score is we take this curve and we standardize it. It becomes a standard curve. This is a normal curve. This is a standard curve where everything is rounded nice and pretty. So instead of having 500 and then going up and down by standard deviation, it looks way better because you just go 0 right in the middle. And then each of these, instead of having 1 standard deviation, 2 standard deviation, blah, 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 or whatever it is, this is just 1, 2, 3, -1, -2, and -3. So getting a z-score is standardizing the data set. So for example, the first data point that we have of 650, we get a z-score of 1.5. And if you look, to plot 650 would go about right here. This would be 650, right? And our standard deviation was 1.5, which if you look right here, 1.5 is the exact same spot on the graph. So we have just standardized the number. That is all we have done. Okay. Now, in order to find the area below, which would be all this, and the area above, is really complicated. However, because it is how it's taught to you, you were allowed to use the tables. I'm not going to expect you to learn calculus to calculate this, and your professor certainly isn't, and that's why everything online just tells you to use the table, because in order to properly calculate this, you need to know calculus, but someone already did that for us, so we have these beautiful, beautiful, beautiful tables, right? Because we're dealing with a positive z number, we would consult this over here, and we go, our number is 1.5, so 1.5 with nothing else. 1.5 is 9332 times 100 to get the percentage. So the area below, so all this, the area below our data point for the first, for 3A, so 650 is the xi. Let's draw a little table here. And then here's the z-score, and the percentage above, and the percentage below, right? So the percentage below here, which we found on the table, is 1.5, is multiplied by 100 is 93.32%. 93.32%. Right? In order to get the inverse, we would take 100, find the difference between 93 and 100, 93.32 and 100, which, so everything above, which is all this stuff that I've just highlighted in white, is going to be 6.68% with a z-score of 1.5, which we already found. Right? So going further down the list to, let's go to a -1, which thankfully is the next one. So the next data point is 400, which we know from just looking right here is going to be -1. The percentage, so because it's a negative, we're going to go over here to the z-score table, and we're going to look for -1. -1 with nothing in the 100th place, or the 10th place right here, is going to be 15.87. So that finds the area below it. So we know that the area below, times 100 obviously, is going to be 15.87%. So right here, area percentage below is 15.87%. Correct? Yes, 15.87%. And then from here, we're going to take 100 minus 15.87. So the percentage area above 400, -1, is going to be 84.13%. It's just that easy, and I will go ahead and I will send over these tables if you don't already have them. But that is how we find the area above the area below. That's how we do number 3. I'll let you do the rest of those. Okay? Great. Perfect. I'm glad we got that done. Okay, and now we are going to really quickly go over the confidence level. I know we already did it, but I feel like I owe an explanation to how we got to do it. If I'm remembering correctly, the mean was 50,000 for the data set, with an 8,000 standard deviation. Is standard deviation. This is the mean. And the sample size, so S, or we could say X, is, N is 100. So I already know, you have it on your notes that I wrote. It's CI equals the mean plus or minus the z-score with standard deviation. I need to get better at drawing it. Z-score square root of n over standard deviation, or under standard deviation. So we're going to find this with a confidence level of 95%. It's actually way easier than I expected. I actually found it. So the way that we do it, in order to find the confidence level, the z-score that corresponds with this confidence level, it's very simple. We take 1 plus the confidence level, which is 95, which is going to be 0.95, because it's a percentage, over 2. That's it. So this is 1.95 divided by 2. Okay? And that is going to give us 0.975. And then with this number right here, we go back to our beloved z-table, and on here we find 0.975. So the z-score is going to be 1.96. 1.96. And that's how we got that. It's way easier than you expect. Yeah, and so then that's how we got this number, which we then plug into there, and we calculated and that's how we calculated the, whatever it's called. I'm trying to remember the name of it. The confidence interval. The confidence interval of 48, blah, 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 to 51, blah, 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 blah. That would be the 95% confidence interval would be that range right there. And that's it. Okay, and welcome to the third part of the video, which is Bob's super spectacular standard deviation thing. So bonus question, number one, I've already written out the data points here. We have 10 data points, but if you read the question, it is a sample. So normal standard deviation, it's going to look scary, but normal standard deviation is calculated as the summation of this minus the mean over n, where n equals the total population, and that is the standard deviation. Okay, but because this is a sample size, it's a little bit different. So this would be if we had everybody, but if you read the question carefully, it says that it is 10 randomly selected students in the class, not the entire population. Therefore, we take this minus 1. That's it. That's the only thing we change. If it was the whole population, it's just the population size. But because it is a sample size of the population, we add that little minus 1. That is the only thing that changed. Don't forget that. Okay. This part is the scariest part. I forgot to add that this is squared, by the way. This part is the scariest part. It looks very scary, but let's go over it really quick, okay? So, first things first, let's do this. Let's solve what is inside of that first, okay? I've already gone ahead and solved all these for ease of time. But x, which is this data point, minus the mean of all these data points, right? The mean, by the way, I went ahead and calculated it, equals 20.5. So we're going to, one by one, each of these. So 18 minus 20.5 is negative 2.5. Okay? And, great, got that. 19 minus 20.5 is negative 1.5. There's two of those. We'll remember that. 1.5. Okay? And you're going to go ahead and you're going to do each of these one by one by one by one. I already have done them all, so I'll go ahead and write that this is negative 0.5. These two are 0.5. These two, because these are the same numbers. This is 1.5. And this one is 2.5. Okay? The next part is that we square it, like it says up here. So we're going to square each of these. And remember, squaring includes the negative, and when you square a negative number, it becomes a positive because you're multiplying it by itself. So this becomes 6.25. These 1.5, negative 1.5s become 2.25 and 2.25. These negative 0.5 and 0.5, all of those will become 0.25, comma 0.25, comma 0.25, comma 0.25, and then same thing on the rest of these. So 2.25 is 1.5 squared. There's two of those. 2.25. Sorry, this is really messy. I'm writing on with a mouse and keyboard. 6.25. Okay, so this is the squared. These are all those numbers squared. So we got this part done now. So the next part, so this is what we have now. This part, this E right here, this scary sigma symbol, this means the summation of. So now we add these numbers together, which I have gone ahead and done the liberty of. The answer is 22.5. So all of this sigma x minus mean squared, all of this, now that we've done all this work, is 22.5. That's it. 22.5. And if we count the sample sizes here, we know that n equals 10, but because it is a sample and not the population, we are going to minus 1. So 22.5 over 10 minus 1, which is 9, is going to give us a standard deviation of equals 2.5. So our standard deviation, this symbol right here, or more accurately, closer to that symbol, or however you can manage to draw it, that's fine, equals 2.5. That's it. That's our standard deviation. Now, for example, if this was the entire population of the class and not a sample size of the class, if this was the entire population of the what we were trying to find, we wouldn't need this minus 1. So instead it would be 22.5 divided by 10, which would change the standard deviation to, I believe it's 2.25. So this is not the correct answer. This is, because we're pulling a sample size. So it is n minus 1 and not just n. Okay? And that is, that's it. That's standard deviation. It's very scary because of this symbol and all this mumbo jumbo here, but I promise, let me make that a little cleaner. I promise it's not scary. It's just kind of tedious, and that is it. That's standard deviation. Bingo.